Welcome back to Statistics. You may have heard the saying that goes, a person is entitled to their own opinion, but not to their own facts. That saying is usually attributed to Daniel Patrick Moynihan, who was a United States Senator. He was a professor, an intellectual, an author, and I think he worked mostly in the 60s, 70s, maybe up until the 80s. And that saying certainly seems grounded in sense, right? Facts, by their very definition, are things that exist independently of us. You can't just make up facts. That wouldn't be a fact you were talking about then. On the other hand, opinions can touch on many things, and sometimes it's not easy to connect opinions to facts. In any case, we live in a free country, and freedom of thought means that you can have whatever opinions you want, right? But still, I would say that saying doesn't go quite far enough. You are entitled to your own opinions, but really, it's pretty difficult to think of an opinion that doesn't touch on some matter of fact. And if your opinions aren't consistent with the facts, well, you're still entitled to them, of course. It's a free country. But if your opinions aren't consistent with the facts, then good luck in trying to convince others to join you in your opinion, or in trying to act on your opinions or beliefs in a way that's in any degree effective. You'll face a pretty steep hill to climb in that case. So we want our beliefs, our opinions, to be at least consistent with the facts, right? And that is one of the uh, tasks that statistics addresses. Is a belief consistent with the facts? And we can already begin to see how our understanding of statistics can give us some tools here to address this question. Is a certain belief consistent with the facts or not? And so that's what I wanted to talk about in this video. Let's take a look. So, putting confidence intervals to work, evaluating beliefs. Confidence intervals, it turns out, can help us in evaluating the consistency between beliefs and facts, data. We know that confidence intervals give us a range of plausible values for a population mean based on observed data and at a specified confidence level. It turns out that we can use confidence intervals to evaluate beliefs about the unknown population parameter mu. And I want to take you through this in the context of an example. Under normal conditions, the net weight of cereal in a certain brand has a mean of 32.4 ounces. But because of small variations in the manufacturing process, the net weight varies from box to box with a standard deviation of 0.2 ounces. So we wouldn't be surprised to find a box that weighed 32.6 ounces or 32.2 ounces or even 32.0 ounces. Those are all within the bounds of, plus or minus one or two standard deviations, and so not to be unexpected at all. Suppose we know that in addition, the distribution of the net weight in a box is approximately normal. So we'll take our variable x to be the net weight of cereal in a box, and it has a normal distribution with mean 32.4 and standard deviation 0.2. The problem is conditions at the manufacturing plant aren't always normal. And by that I mean usual. Problems with the manufacturing machinery can result in boxes of cereal that are either underfilled or overfilled. And this is a problem This would result in a net average weight that could either be less than 32.4 or greater than 32.4 ounces. The manufacturer would like to be able to detect whether such a problem is occurring and hopefully fix it. How could we do this? Well, a very common and sensible idea is simply to periodically monitor the manufacturing process by taking a random sample of, say, N boxes from the production line and weighing them. If you did that and looked at the sample mean weight, and that turned out to be significantly different than 32.4 ounces, then you might have a red flag. There might be a problem with the manufacturing machinery. Notice that this fits totally within our sort of paradigm of estimating population parameters with sample statistics. The boxes you take from the production line and weigh would be the sample, and you're trying to use the sample average to estimate the true population average weight, which hopefully is 32.4 ounces, but if something's going wrong, it may change. So, how would this work? Suppose, for instance, that we took SRS, a simple random sample, of size n equal 25 boxes from the production line, and we found a mean weight in the sample of X bar equals 32.5 ounces. So 32.5 ounces is a little heavy, right? The mean was supposed to be 32.4. Would this give us good reason to suspect that something has gone wrong with the manufacturing process? I mean, you can kind of imagine two quality control engineers, say, who are doing this process, and they would look at that sample mean weight of 32.5 ounces, and maybe they would have different beliefs. Maybe the first engineer says, look, the mean is supposed to be 32.4. I realize that. We got a sample average of 32.5. That does look a little bit heavy, but come on, we know that there's variation in the amount of cereal in each box. In fact, we know it has a standard deviation of 0.2 ounces. Are we really that surprised to get a sample mean of 32.5? I don't think so. I think everything is working fine. We should just continue production. But then the second engineer jumps in and he says, now wait a second, 32.5 ounces, that really is high. The mean is supposed to be 32.4 and we're getting 32.5. I believe that something is actually wrong with the machinery. We should shut down production and get this fixed, otherwise we're going to lose money. So there you have a set of facts, namely the sample of 25 boxes that weighs 32.5 ounces per box on average, and two conflicting beliefs about the facts. The first engineer thinks that that kind of variation is just what you would normally expect in a manufacturing process like this one, while the second engineer believes that something indeed is amiss, that the 32.5 is indicating that something's wrong. So, yeah, both engineers are entitled to their opinions about this, but which one is supported by the facts? Whose opinion is actually consistent with the facts at hand? Well, let's look a little bit further and see what we can find out. So, if you're just looking at this sort of casually, you might be inclined to agree with the first engineer. 32.5 is not that different than 32.4. Maybe things are just okay. A little bit of variation here, right? We'll see. But I want to just point out that the same question would recur even if the numbers were different. Suppose you got 32.37 as the sample average weight. That's even closer to 32.4, right? So if the first engineer had a point in the 32.5 ounce case, he has even more of a point in the 32.37 ounce case. But what would the answer be? And you could continue to come up with different values for that sample weight and ask the same question: does this really indicate something's wrong? Well, fortunately, statistics does give us a way to address this problem. And let's take a look at how it works. So essentially, there are two beliefs that are possible in this situation. We call those hypotheses in statistics. The first is that the production machinery is working properly. Nothing is amiss, all is well. Continue about your daily lives. This is the opinion of that first engineer. I'm denoting this belief by H0. That means hypothesis zero. Actually, we'll call it the null hypothesis for reasons we'll get into in a second. The second possible belief is that, yes, indeed, something is amiss. The production machinery is malfunctioning. That's again a hypothesis about the reality that could be going on here. I'm calling that H sub A. Again, the H is for hypothesis, and I'll explain the subscript here in a minute. But it's important to point out that we can restate both these beliefs purely in statistical terms, purely in terms of the population mean mu, the average amount of cereal in a box. H0, the belief that the production machinery is working properly, is equivalent to the assertion that the true population mean is just what it's supposed to be, 32.4 ounces. While HA, the belief that the production machinery is malfunctioning is equivalent to the hypothesis that the true mean value is no longer 32.4, but that the mean assumes some different value. These two hypotheses have special names in statistics. The first is called the null hypothesis. That's why we have the subscript 0 there for null. The null hypothesis we'll see in future examples essentially it's the hypothesis that nothing is amiss, that there's no difference between the current situation and whatever we're calling the normal situation. That's the null hypothesis. It's always, for us, a hypothesis of equality. It'll be a hypothesis that the mean, or whatever parameter we're looking at, is equal to something. The second hypothesis is called the alternative hypothesis. It's the hypothesis that you believe will be true provided that the null hypothesis is not. So in this case, it simply means that the true mean amount of cereal in a box now is no longer 32.4, it's something else. So we have our two hypotheses, and these really are competing hypotheses. They both can't be true at the same time, right? So I've used the word versus there intentionally. There's an analogy here that I'd like to give that that kind of could help you as you think your way through this, and it's a courtroom analogy. Because in a courtroom, say in a criminal trial, there are also two beliefs that are under consideration. The first is the belief that the defendant is innocent of whatever crime he's been accused of. And the alternative is that he's guilty. To map it to our situation here, the hypothesis that the defendant is innocent would be the null hypothesis, right? It's the hypothesis that there's nothing wrong, that there's no change in what's, from the normal situation here. That's the analog to the assumption of innocence in a criminal trial. While the assertion of guilt in a criminal trial is the alternative hypothesis in our scenario. Now, in a criminal trial, these two hypotheses don't have exactly the same standing. In the United States and in many other countries, there is an assumption of innocence at the beginning of a criminal trial. That is, the jury is instructed that until proven otherwise, the defendant is assumed to be innocent. And it is the job of the prosecution to overcome that presumption. And how does the prosecution do that? Well, they present facts and put into evidence facts that are inconsistent with the presumption of innocence, right? So if I've been accused of murder, initially the jury is told to regard me as innocent. But as the prosecution produces evidence, that presumption may be overcome, right? If that evidence is truly inconsistent with the presumption of innocence. So for instance, if there's video of me killing the suspect, that's pretty strong evidence that would tend to be inconsistent with my with an assumption of innocence on my part. Well, we're going to operate in more or less the same kind of fashion in statistics when evaluating beliefs. That is, we're going to assume, more or less for the sake of argument, that the null hypothesis is true. And then we're going to look at our data and ask, is it really consistent? Is our data consistent with the null hypothesis? And if it's not, that tends to argue in favor of the alternative hypothesis. So it's very much like a courtroom sort of proceeding that we're going through, at least in terms of the logic that we're using. So for the sake of argument, let's assume the first engineer was right. Let's assume, again for the sake of argument, that the true population mean weight of cereal boxes coming off the assembly line is still 32.4. With that assumption in play, let's ask a question now. Is our evidence, which is our observation of a sample mean value of 32.5 ounces, is that consistent with that assumption? In other words, under the assumption that mu is indeed 32.4, would our observation of 32.5 as a sample mean be considered typical, more or less what you would expect? Or would it be an unusual or extreme observation? If the observation is typical, then there's no reason to question the assumption that mu equals 32.4, right? On the other hand, if the observation is unusual, given the assumption that mu equals 32.4, that does give us some basis for questioning our assumption. So to answer that question, is x bar equal 32.5 typical or extreme, we need to look at the sampling distribution of x bar, because that gives me the sort of spectrum of all possible values of x bar, and that gives me a basis for judging whether my x bar is extreme or not. So how can we do that? Well, fortunately, our assumption, for the sake of argument again, that the null hypothesis is true helps, because the null hypothesis is giving me the value of the mean, 32.4. If that's true, then I know the mean of the sampling distribution, since the mean of the sampling distribution, mu of x bar, is the same as the mean in the population. This is from our previous work. Moreover, we know that the standard deviation in the population was 0.2 ounces. And knowing what we know about sampling distributions, we know that the standard deviation of the sampling distribution would be the standard deviation in the population divided by the sample size. So that's our 0.2 divided by the square root of 25. And that turns out to be 0.04 ounces. So the standard deviation of x bar is much smaller than the standard deviation of the weights of individual boxes of cereal. Moreover, we know that the population distribution of, the weights of cereal in boxes is normal, because that was given to us. So this tells us we can use the normal distribution for the sampling distribution, right? Because if the population distribution is normal, then we know the sampling distribution of x bar is normal for any sample size. So here's the sampling distribution of x bar. It's normal with mean 32.4 and standard deviation 0.04. Now, let's ask, where is our observation in the sampling distribution? Well, there it is. Would we consider that a typical value in the sampling distribution, or is it more of an extreme value? I think you can probably see the answer. Excuse me. But before we answer it explicitly, let's define a little more precisely what we mean by extreme. Let's say that extreme means outside the middle 95%. By that criteria, our x bar is certainly extreme, right? The graph shows you the shaded tails are the parts of the distribution that are outside the middle 95%, and our x bar observation is right in there. It is in that right tail a good ways in fact. So that says that yes, our observation was rather extreme given the assumption that the true mean is 32.4. In fact, and we'll expand on this a little later, but we can sort of quantify exactly how extreme it is. In this slide, I've shaded all the observations from the sampling distribution that would be at least as extreme as mine, in the sense of being at least as far outside that middle 95%. And the area of that shaded region is 1.242%. That means our observation of x bar equal 32.5 was in the top 1.242% of all possible observation in terms of extremity. So actually, our observation is pretty extreme. It would be very unusual if mu were truly 32.4 to see a sample mean as big as 32.5. So what do we make of all this? Well, remember, this is all assuming that the null hypothesis that mu equals 32.4 is true. There is another hypothesis in play, and that's the alternative hypothesis. If that were true, then it leaves open the possibility that our x bar might not be that extreme at all, right? Because the alternative hypothesis is that mu is not equal to 32.4. That leaves open the possibility that mu is actually a little bit higher, as I've shown here in this graph. The curve on the right there has mu shifted over a bit to the right, and now if you think about x bar in that distribution, where mu is actually not 32.4 but some higher value, our x bar is not extreme at all in that mu distribution. In fact, it would be very typical. That suggests that our data is not really consistent with the null hypothesis and is consistent with the alternative hypothesis. So since our x bar value is so extreme under the assumption that mu is actually 32.4, it counts as strong evidence against that very assumption and evidence in favor of the alternative belief that mu is not 32.4. In other words, the second engineer was actually right. X bar equal 32.5 is strong evidence against the belief that the production machinery is working normally and in favor of the belief that a malfunction has in fact occurred. So how does this relate to confidence intervals? Well, think about why x bar was outside of that middle 95%. It's because it was more than 1.96 standard deviations away from the mean of 32.4, right? 1.96 is the number of standard deviations, right? You need to the left and right of a mean in order to get that middle 95%. And our x bar was more than 1.96 standard deviations away from 32.4. This means that 32.4 is not in the 95% confidence interval for the true mean mu, right? Because that 1.96 standard deviations is precisely the width of that margin of that confidence interval. There you see the confidence interval in the slide going from 32.42 about to 32.58. That's our 95% confidence interval for mu. And the value in the null hypothesis of 32.4 is not in there. In fact, it's true that no value outside of the confidence interval is a plausible value for mu at the 95% confidence level. And why is that? Well, it's because values of mu that are outside that confidence interval would place x bar outside the middle 95% of the sampling distribution. And I'm illustrating that with this slide here. Here we have a mu that's, it looks like about, it's less than 32.3. I'm thinking about the mean of this normal distribution you see here. It's quite a bit less than 32.3. And you see the middle 95%, and you see shaded the tails that correspond to extreme values. And x bar equal 32.5 is definitely in the tails of this normal distribution here. That's with a mean of, it looks like something like 32.28 or something. Now, if I move that hypothesized value around a little bit, so now I'm taking a mu that's slightly bigger, it's still the case that our x bar value is in the tails of that normal distribution. It's not in the middle 95%. As I move that normal distribution closer now, so think about the mean of the normal distribution, that's your mu. Right now it's sitting at about 32.36, maybe a little bit bigger. That's not a plausible value for mu because that value of mu would put our x bar way out in the tails of the sampling distribution, and that's just highly unlikely. You have to keep bringing the mean closer to our x bar value to get it closer to that middle 95%. So here, now the mean of our, the mean looks like it's about 32.41 or 42, and x bar is still in the tails. X bar is not in the middle 95%. And so this value of mu, again, it looks like about 32.41, is not a plausible value because it puts x bar too far out in the tails. But we keep bringing it in closer, and all of a sudden you get to a point where the mean is at a point at which it places our x bar right at the boundary of the middle 95%. That is the boundary of our confidence interval too. That's the value mu equal 32.4216. And that is a plausible value for mu because, well, just barely. It's like a boundary value because it places x bar right at the boundary between the middle 95% and those tails. Move mu a little bit closer, and now x bar is comfortably within the middle 95% of the sampling distribution. So notice these values of mu correspond to values in the confidence interval. They're highlighted in green on the graph. And all of them have the property that the observed data is typical under these hypothesized values of the mean. You keep sliding the confidence interval over, and all of a sudden you get to a point where you're back in the tails again, right? Now it looks like my mu is maybe 32.6 something, and once again, my x bar is out in the tails, and so this would not be a plausible value of mu given our observed data x bar, and neither would anything else to the right of that. So in other words, given x bar equal 32.5, the plausible values at 95% confidence for the true mean are precisely the values inside the 95% confidence interval. And what makes them plausible is that they place our observed x bar within the middle 95% of the sampling distribution. So we say we are 95% confident that the true mean is in that region. So let's summarize. A level C confidence interval for mu gives the plausible values for mu at a confidence level C given the observation of x bar. Values of mu that are inside the confidence interval would place the observed x bar inside the middle C% of the sampling distribution, meaning that the observed value would be considered typical or not extreme at level C confidence. Values of mu that are outside the interval would place the observed x bar outside the middle C% of the sampling distribution, meaning that x bar would then be atypical or extreme. And finally, in terms of evaluating beliefs, at confidence level C, we should reject the belief that mu has a particular value if that value does not fall into the level C confidence interval for mu. So I hope this has given you a little bit more insight into why we call the values in a confidence interval the plausible values for mu. They're plausible because any other value would make mu an extreme and very unlikely observation. And you can't just go around claiming that all your observations are extreme and very low likelihood, and yet I saw them anyway. We'll have more to say about this, much more in fact, because we've basically broached the subject of significance testing in statistics, which is an important part of inferential statistics. And so this can be also thought of as sort of an introduction to that. In any case, let me know if you have questions. As always, stay safe, and we'll be back at you again soon. Y'all take care.